All right, we're good to go. So, let's start with questions. Had some questions from people on homework, especially around the factorial inductive proof. Factorials are weird, but they're kind of cool too. Um, but mostly for the homework, I'm looking for the structure of your proofs. I want to make sure that you're proceeding logically, that you're showing a base case, that you're proving the inductive step, which means you're assuming the inductive hypothesis, which is typically P of n, and then you're working logically to show P of n plus 1. I'm not necessarily as concerned with, are you an expert in factorials and able to find that one magic trick for turning this expression into that expression. That's cool to be able to do, but it's really an exercise on induction and inductive proofs more than factorials. So, for example, if I was only grading one problem, that probably would not be my choice, and the factorial magic would not be, a significant piece of the grade. Um, but yeah, so I'm looking for setup and stuff like that. And yeah, I think induction is pretty cool too. All right, so let's talk really briefly about the next homework. So I posted homework 8, and it comes from the original textbook, but here's a synopsis of them. So, 4 sections: 2, 1, 2, 3, and 4. So 2.1. 3 questions. Certain shirt comes in 4 sizes and 6 colors, and you have a choice of a dragon, an alligator, or no symbol on the pocket. How many different shirts could you order? So that's a pretty direct product rule, right? So think about what's the task of choosing a shirt. Well, first you choose the size, and then the color, and then the thing to go on the pocket. Um, so that's a product rule. Um, Having a picture taken of its 6 officers, 2 rows of 3 people. How many different ways can the 6 people be arranged? So think of a succession of putting somebody in the first position, and then the second, and then the third, and then going to the second row and doing the same thing. And then question 15, same idea, right? So you're ordering a meal, and you have choices you can make as to the entries. 2.2, 3 different prizes, and there's 1,000 raffle tickets. How many different ways can the prizes be distributed? So this will get into some of the things that we're doing today. You can break these down to products and sums. We're going to talk about permutations and combinations. And these have to do with a number of ways to typically make some selection out of a larger set. So here we're trying to pick 3 prize winners out of 1,000 raffle tickets. And it's different if the prizes are identical or if they're the same. If there's 3 different prizes, right, then you don't just need to know which 3 people win the prizes, but which person wins prize A, which wins B, and which wins C. So we're going to look at questions where order matters or doesn't matter, right? And that'll be the difference between permutations and combinations. And then basketball questions. So you have 15 players and you're trying to fill 5 positions. And if we assume each position is unique, right, then this is like awarding the different prizes. You have to know which player fills position 1 and 2 and 3 and 4 and 5. And then part B, we've only got 2 people who can fill one particular position called the center. So think of that as a succession of tasks, right? First, figure out who takes the center position, and then figure out the problem for the 4 remaining positions. Oh, and I skipped one. 8-letter words formed from 26 letters in the alphabet. how many ways can you do that? And I think the two interpretations of this problem are, you know, if we don't use what we know about words, and we just say, here's 26 letters, how many words can you form? Well, if you had 26 blocks with letters written on them, how many words could you form? Well, you could only use a letter once in that case, right? Or, you know, refrigerator magnets shaped like letters. You got 26 of them, how many 8-letter words can you form? Well, you know, if you can only use a letter once, you get a certain set of words. But if you're allowed to just, you know, draw any old 8-letter word using letters, you could have repetitions. And the question's ambiguous as to which of those applies, so answer both questions, you know, answer for both assumptions. And then 90 people, and this is an inclusion-exclusion question, so 90 people, some of them play tennis, some swim, some do both. How many people participated in neither? And then 2.4, these relate to combinations, which is arrangements of things where the order matters, and we're going to talk about that today also. And the first one is you have to choose 3 faculty and 4 students, right? Out of 10 faculty and 25 students to choose from. And you want to know how many ways you can do that. So that's a product sum rule. Subsets, well, I didn't copy this correctly, but it's correct in the book. Subsets of the numbers 1 through 10, how many subsets contain at least 7 elements? So this is another product sum rule, right? And sometimes these questions come down to how do you break it down into subproblems, right? So if we want to know how many subsets of the numbers 1 to 10 contain at least 7 elements, well, you might break that into 4 problems. How many subsets contain exactly 7 elements? How many contain 8? How many contain 9? How many contain 10? And now to find a subset that's described by this question, you can find either a subset in that first form or a subset in the second or third or fourth. So it's a sum rule. But to answer each of those questions, you're going to have to use combinations, permutations, product rule. Okay, 5 is a straightforward binomial expansion, which we'll talk about probably on Friday. And 13, think about this. This is a geometric problem where you have n points drawn on a plane. No 3 of them are collinear. And you want to know how many lines you get by connecting pairs of those points. So question, can we try one of these? Sure. I mean, that's pretty much our drill for today is to work through these things. So let's do a product sum rule as an example. So let's say you have to pick 2 of 5 required courses and then 1 of 3 electives. So you're registering for classes. And there's 5 required courses and you have to take 2 of those. And then there's 3 electives and you can pick any one of those. So you're going to sign up for a total of 3 courses. But you can't just take 3 electives this quarter, right? So you've got to take them from this particular set of criteria. So let's do this as a sum problem, right? Let's first do this task and then do this task. And the total number of ways to register for classes will be the sum of the number of ways to do this and the number of ways to do that. All right, so how do we pick 2 of 5 required courses? Well, let's break that into 2 subtasks. T1, pick the first course. T2, pick your second course. Well, there's 5 required courses. How many ways can I pick my first course to take? There's 5 possible ways because I can take any of those courses. And if we assume you can only sign up for a course once, You can't take two courses. You can't take the same course twice in one quarter. I tried doing that. It doesn't work. We can't pick that same course we already picked for task 1, so now there's only 4 courses we can choose from. So the number of ways we can complete task 2 is 4. And so the total number of ways that we can do this first circle task is 5 times 4, which is 20. After we've picked our 2 required courses, we're going to pick one of 3 electives. Well, how many ways can we choose an elective? Well, there's 3 ways to do that, because we only have 3 electives. And then the total number of ways is the sum rule, 20 plus 3. There's 23 different schedules you could come up with for registering. So that's an example of sum rule, product rule, which is like the questions in 2.4. So it's, oh yeah, I blew it. It's not a sum rule. Right, so if this is and, yes, then it's a product rule on there also. So it's 20 times 3. So a total of 60 courses. But if it was set up that you could take 2 required courses or 1 elective, right, then it would be 23. So that would be a sum rule. But yes, you're absolutely right. Thank you for pointing that out. So the way I wrote it, that's actually a product rule. 60 schedules you can come up with. But if it's an or, right, either take 2 required courses or 1 elective, add together the number of ways to do each of those. Let's see, would it be okay to do this process in reverse? I think so. The order in which you do these shouldn't matter in general. Yeah, that should work fine. All right. Well, let's go on to permutations and combinations. So this is going to be the bulk of the rest of this unit on counting, and we're going to start off talking about permutations. Okay. So let's start with some definitions. So a permutation and the difference between permutations and combinations is order. So a permutation is an ordered arrangement of objects. So it's an ordered arrangement. It's a case where you know, you're standing people for a picture, but the way that they're situated is significant. Okay, so given n objects, we can describe what's called an R permutation. So an R permutation is an ordered arrangement of R of those objects. All right, so let's see some simple examples. So there's a set of 3 objects, A, B, C. And a set is unordered, right? A set is just a collection of objects. But we can put these in a particular order. So A, B, C, that's a permutation of those elements. So is ACB, so is CBA. So these are permutations. A 2 permutation would be an ordered arrangement of 2 of these objects. So examples of 2 permutations would be AB, BA, BC, CA, and so on. So those are 2 permutations. Okay, pretty straightforward definition. So it's an ordered arrangement. So for example, let's say you have 5 people and they're going to stand in line. So 5 people standing in line, these 5 people are distinct, okay? And the order in which they stand in line is significant. So how many different ways can you arrange these 5 people in a line? And we can use the product rule. So we can break this into a set of 5 tasks. Task 1, choose the first person in line. And then task 2, choose the second person in line, all the way down to task 5, choose the last person in line. And how many ways can you choose the first person in the line? Well, any of those 5 people can go first, so there's 5 ways to do that. But to choose the second person, you've already taken one person and put them in line, so now you only have 4 people left. And this goes down until N5. You've only got 1 person left, and so there's only 1 way you can choose somebody to go in that last position. So this is just the product, so it's 5 times 4 times 3 times 2 times 1. So yes, as someone just said in chat, this is 5 factorial, which is 120. Okay, and this example and the next example are going to lead us to a general formula. So the question gets a little different. If you have a group of 5 people, but you're going to put 3 of them into a line, so now task 1 is the same as before. Task 2, pick the second, and task 3, pick the last. And again, the number of ways we can choose who goes first in line is still 5. Number of ways to choose who goes next is 4. The number of ways to choose who goes last is 3. But we're only putting 3 people in line. So the total number of ways is 5 times 4 times 3, which is actually 60. Right, we have fewer arrangements that we can make, but this is somehow related to that, right? There should be a connection between them. So here's what we're going to do. We're going to notice that this number is basically our original number, 5 factorial, but with the tail of this divided out. Right? So one way to write 5 times 4 times 3 is 5 factorial divided by 2 factorial. Yes, exactly. Perfect. Someone got that in chat. So let's play with that formula for a little bit, and then let's generalize this. Suppose I want to write 7 times 6 times 5 times 4. I can write that as this big long product divided by this smaller product. And really all I'm doing is I'm taking this and I'm multiplying by 1. Right? 3 times 2 times 1 divided by 3 times 2 times 1. That's just 1. But when I write it like this, it gives me the advantage of being able to write the numerator as 7 factorial and the denominator as 3 factorial. Now if I just wanted to do 7 times 6, I can do the same thing. And here it's 7 factorial over 5 factorial. Alright, so if we multiply integers starting from 1 going up, that's just a plain old factorial. If we multiply integers starting from n and working down but stopping at some point, that's a quotient of factorials. So yeah, someone suggested n factorial over n minus the subset size factorial. That's exactly right. So in general, if we want to do 7 or n times n minus 1 times n minus 2, and we want to do r of these, it's going to be n factorial over n minus r factorial. There's no real science or intuition to that. It's really just sort of a numerological trick that works well for rewriting, something like this using factorial notation. But it turns out that this is exactly the situation when we have an R permutation. In particular, an R permutation of n objects. Because if we break it into a product rule, the first object can be selected n ways, the next n minus 1, the next n minus 2, and so on. And we have R of these terms because we have R subtasks because we're selecting R objects. So this gives us our first fancy schmancy formula for permutations, which is the following. And we use P to represent permutations. P of n comma R equals, and that's a symbol for the number of R permutations of n objects. And this is equal to n factorial over n minus r factorial. So that's one for the record books. That's a good formula to know. And once we have this formula, we can just go to town with it and do all kinds of calculations. So let's say that you're playing a card game and you're going to be dealt 5 cards out of a deck of 52. And let's say the order in which the cards appear is important, right? So getting a Jack, Queen, King is different from getting a Jack, King, Queen. So how many ways can we arrange 5 cards out of 52? It's just going to be the number of 5 permutations of 52 objects, which will be 52 factorial over 47 factorial. So that's really all there is to permutations, but we can use this one formula in a lot of different situations. Okay, so for example, you have a running race. You have 10 runners, and you have 3 medals for first, second, and third place. So you have, you know, gold, silver, bronze, and you want to know how many possible outcomes there are to this race. And it's simply asking how many 3 permutations are there of 10 objects, right? Because each outcome will be a particular arrangement of exactly 3 of these 10 runners, where you put them on the award podium. You know, there's first, second, and third place. And so how many ways can you pick 3 of these 10 and arrange them in that order, right? So number of outcomes is just p10 comma 3, which is 10 factorial over 3 factorial, which you can multiply out, and it's some big number. $604,800. That's written down. I didn't do that. All right. If you have a group of 6 people and you're trying to sit them at a table, and you want to know how many ways you can do that, well, that's the question of how many ways are there to arrange 6 people taken from a group of 6, which according to our formula would be 6 factorial over 6 minus 6 factorial, which is 6 factorial over 0 factorial. All right, so here's a good place for a little sidebar. What is 0 factorial equal to? Because if it's 0, my 7th grade teacher is going to come over here and yell at me. Right? 0 factorial is equal to 1. Why is that? Excellent. So yeah, we define factorials usually as, you know, n factorial equals the product of all integers up to and including n starting from 1. But 0 factorial doesn't really work with that definition, because there's no sequence of integers starting from 1 that ends with 0. And so we need to do something different to find 0 factorial. And in fact, we can actually calculate things like 1/2 factorial. We can find factorials of fractions. We can calculate pi factorial. So how does this work? So as someone just said in chat, there's this thing called the gamma function. So this is one of the few times you'll see some calculus in this class. Well, we're always doing calculus, but one of the few times I'll show you an integral in this class. But everybody should have seen the gamma function as well as Stirling's formula. So this comes out of a big, horrifying definite integral, and we're not going to work with this integral. But it's pretty cool. So the gamma function is the integral from 0 to infinity of x to the z minus 1 e to the minus x dx. All right. So this is the gamma function of z, right? So it's an integral of x raised to whatever your value of z is times e to the minus x dx. And it's a hard function to find an antiderivative of, but numerically we can calculate the value of this. And it turns out that, you know, for positive integers, this follows the curve of a factorial, right? And gamma x is actually x minus 1 factorial. So gamma 1 is equal to 1. Gamma 2, if we could take this up a little higher, would actually be equal to 6. And gamma 3 would be 24, and so on. And so if we use this as a stand-in for the gamma function, we can easily find what gamma of 0 is, or what 0 factorial is. It's just gamma 1, which is equal to 1. And then if we try to calculate factorials for numbers smaller than 0, well, they start increasing again. But negative integers, the factorial blows up. And in between, we get these funny shaped curves that get, you know, steeper and steeper. And it's a cool function. It's got really odd behavior. But it's what we sometimes call, you know, an extension of a function, or an analytical extension. It matches our notion of gamma function on positive integers, and we have good reason to treat it as being the value of factorials for non-positive integers, meaning negatives or fractions. And this has lots of cool properties to it. If you look at particular values of it, right? So you can show this, right? That the value at x plus 1 is x times the value at x, so that's why it matches factorials. And if you look at particular values, so gamma of 1/2 is the square root of pi. So how awesome is that? Right, so gamma 1/2 would be factorial of, if I've got it right, I might have it backwards, minus 1/2, I think. Right, so there's just boundless coolness in here, right? And if you start making graphs and looking at the derivative of the gamma function, you get all of this awesomeness popping out also. So anyway, that's a little bit about factorials. All right, so back to permutations and combinations. Oh, I know, math is so cool that way. It's like you can see things and you just know there's something cool there, even if you don't know what's actually going on. That's the discovery of mathematics, right? I mean, you see a result and it strikes you and you want to understand it, and it's the quest for the understanding of why something is the way it is. That's, you know, mathematical discovery. So you make a Mandelbrot set, and, you know, from like a very simple quadratic equation, you get these incredible sets that you know, lead you to all these deep philosophical insights about connectedness and so on. And you want to understand where that's coming from and what it means, right? So you can dig into it mathematically. Yeah, math does rock. I totally agree. All right, so this is totally legit now, right? If the number of ways to take 6 things and arrange them out of a group of 6, that would just be 6 factorial over 1. That's just our good old 6 factorial. Right, so it's n factorial over n minus r factorial. All right, so we can re-evaluate some of our product rule questions and do them more concisely using this idea. For example, you know, number of 5-letter passwords is just P26, 5. But this is looking at picking 5 letters and then putting them in a particular arrangement. So this is actually 5-letter passwords without repetition. So this is like when you're told you can't use the same letter more than once in your password. someday that'll become like a password rule. That's when I'll like change professions. Right? So when you try to think of something as a permutation, remember we're taking a collection of objects and arranging them. Okay. Now if we and this is 26 factorial over 21 factorial. If we didn't have this restriction on repetition, then it's just 26 choices for each letter, which is just 26 to the 5th. That's a good point. It would be less secure if you weren't allowed to use repetition. And you can see that here too, right? With repetition, you've got 26 to the 5th. Here you've got something significantly smaller. But that never stopped someone from imposing password rules. And so sometimes we can use this same idea, but we need to rephrase our problem. So for example, how many arrangements are there of the following letters where A, B, C must appear? In other words, how many ways can we arrange these 8 letters if we impose the requirement that A, B, C have to be right next to each other in that order? And there's easier and harder ways to answer this question. The harder way would be to find, all the ways to arrange A, B, C, D, E, F, G, H, which is, just 8 factorial. And then try to divide out, the number of ways that don't include A, B, C next to each other. But there's an easier way to think of this. Since we're trying to arrange these 8 letters, but we're requiring that A, B, C always be next to each other, we could think of this as a question of how many ways can we arrange the following symbols: A, B, C, D, E, F, G, and H. And now we simply have 6 objects we're trying to arrange, and we can do that a total of 6 factorial ways. So sometimes you'll come across a question and the solution is more about changing your view of the original problem into a problem that's easier to solve. Right? And this is, of course, the essence of programming. Right? We don't have a web browser instruction in Java. Well, we almost do. But we take the task of making a web browser and we break it down into other tasks that we can do, right? So here we're taking this question and saying, oh, well, that's just 6 objects that we have to arrange, and then the answer is very straightforward. All right, so that's permutations. Okay, permutations are ordered arrangements. All right, the other side is combinations. So a combination is an unordered arrangement. So permutations are ordered, combinations are unordered. Okay, for example, pick 3 people from a group of 5. So you have 5 people in a room, you want to pick 3 of them to go outside or something. And the order in which you pick is not important. The only question is how many ways can you choose 3 people? Well, so we could break this into a set of tasks, right? T1, pick first person. T2, pick the second person. T3, pick the third person. And there's 5 ways to do that, and 4 ways, and 3 ways. And that's 5 times 4 is 20, that's 60 ways. But this is not our final answer, right? Because this is the number of ways we can pick someone to be first, someone to be second, someone to be third. Well, let's suppose our people are named A, B, C, D, E. Right, so 5 people, A, B, C, D, E. And suppose we pick, persons A, B, and C. Well, when we do the product rule, right, this particular selection corresponds to picking A to be the first person, B to be the second, C to be the third. But in practice, if we had picked person C first, and then B, and then A, we've got the same group of 3 people. So this 60 counts each of these as a distinct way to pick 3 people. But if we don't care about the order, right, these both represent the same choice. And in fact, so does ACB, and CAB, and BCA, and BAC. So all 6 of those correspond to the same choice. And similarly, if I had chosen persons, B, D, and E, well, that's the same choice as if I pick BED, DBE, DEB, EBD, or EDB. So 60 is too big a number, right? Here's 10 ways to rearrange these objects, but these actually only correspond to 2 particular selections of 3 people. Sorry, there's 12 ways, and it corresponds to 2 particular ways. So how do we adjust this? How do we bring this down to the actual number of ways that we can choose 3 people ignoring order? It's 60 over the number of ways to arrange 3 people. So this is a little more complex of a formula. So the number of combinations of 3 people taken from a group of 5, instead of writing a P, we write this as C, 5, 3. That's the number of 3 combinations of 5 objects. And it looks like the original number of permutations, but divided by the number of ways we can rearrange those 3 people that we pick, those 3 objects. Right, so remember, this is unordered. And that's what combination means. So how many ways can we arrange 3 objects? Well, how many ordered combinations how ordered permutations are there of 3 objects if we're going to pick 3 of them? Right, this is just P 3, 3. All right, well, let's think about this. P of 3 comma 3 is just 3 factorial. Right? So we could write this a little more simply as just P5 comma 3 over 3 factorial. All right, so for the problem we just did, 60 people, but there's 6 ways to arrange 3 people, so there's 10 combinations, 10 ways we can pick 3 people out of a group of 5. All right, so let's generalize this. Number of ways to pick r people from a group of n is p n comma r divided by r factorial. In other words, it's just the number of ordered combinations divided by the possible number of orders. Okay, so that's the difference between a permutation and a combination. If you divide out the number of rearrangements, you find the number of combinations. And remember, we have a formula for p of nr. This is n factorial over n minus r factorial. And then we just multiply by r factorial. And so there's our formula for the number of r combinations of n objects. And we also have a different notation you'll see for this. This is sometimes written like this. nr in parentheses, no line in between, because we're not dividing n by r. It's a different symbology. And it means the number of r combinations of n objects. All right, so let's play with that for a few examples. So there's our formula. So number of 5-card poker hands. So when you play poker, you're dealt 5 cards out of a deck of 52. The order in which you get those 5 cards does not matter, right, if you're doing 5-card draw. So you get 5 cards, and all you care about is what are the 5 cards. And it doesn't matter if you got this card first, last, or in the middle. So how many 5-card hands are there? It's just the number of 5 combinations out of 52, which we could also write like this. And that's just going to be 52 factorial over 47 factorial times 5 factorial. And if you're curious, that's 2,598,000 and change 960. It's not all that many. All right, pick 5 people from 10. Well, that's 10, 5, which is 10 factorial over 5 factorial times 5 factorial. All right, let's look at 2 edge cases. Suppose you want to pick 10 people out of a group of 10, and the order does not matter. This would be 10 factorial over 0 factorial times 10 factorial. That's just 1. And that's the right answer, right? Yes, all of these are unordered combinations, right? How many ways can you pick 10 people from a group of 10? There's only one way, which is to pick all 10 people. If we don't care about who gets picked first, second, third, we're just looking at how many, collections of 10 people are there from a set of 10, it's just one possibility. You just choose everyone. And that checks out with our formula because 10 choose 10 is, equal to 1. Suppose I go to the other extreme and I say, how many ways can you choose 0 people from a group of 10? Well, that's going to be 10 factorial over 10 minus 0 factorial times 0 factorial. That's 10 factorial over 10 factorial. That's again 1. And yeah, if your task is to choose no one from a group, how many ways can you complete that task? Only one way, which is don't choose anyone. So these edge cases work out. But they also start to suggest something else, which is symmetry. Symmetry is another one of these things that when you start bumping into it, pay attention. Although asymmetry is even better. So let's say pick 3 people from a group of 10. And this is sometimes called 10 choose 3. So you'll see lots of notation. So 10 choose 3 is 10 factorial over 10 minus 3 is 7 factorial times 3 factorial. That's the number of ways we can pick 3 people from a group of 10. But if your task is to choose, say, 3 people to go out to dinner with from a group of 10, there's an analogous task you could do, which is choose 7 people from a group of 10 to not go out to dinner with. And if I choose 3 people to go out to dinner with, or I choose 7 people not to go out to dinner with, it's the same thing, right? The number of ways I can pick 3 to dine with is the same as the number of ways I can pick 7 to not dine with. So this should be the same thing as 10 choose 7. Well, is it? 10 choose 7 is 10 factorial over 10 minus 7 is 3 factorial times 7 factorial. It's exactly the same thing. All right, so there's symmetry in here, and we'll see a particularly cool form of that in a little bit. So questions so far? Someone said colon Q. I thought they were quitting on the subject, but I think they typed in the wrong window. Yeah, I do that all the time. I'm always sending bash code and C code to my girlfriend, but she does it too, so it works out. All right. Good time reminder. There is no class on Wednesday. So Wednesday is Veterans Day. Classes don't meet at Clark. So we will meet again on Friday, but not on Wednesday. Yes, I agree. For love to flourish, you must share code. That's a truism. So how many 8-bit numbers contain exactly 3 ones? If you were to write out an 8-bit number and count up the number of ones, how many of them would contain exactly 3 ones and, presumably 5 zeros? So something like 6 factorial, but not exactly that. Think about combinations. And questions like this, it's largely about how do we think of this in terms of combinations or permutations. So yeah, that's a correct answer. How did you get that? Right, so we can think of this as 8 choose 5. 8 choose 5 is basically saying we have 8 bits. So, here's the 8 bits we're going to fill in our number. And our question is, which 5 of these will contain zeros? So, maybe I'll put a 0 here, 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 and here. Well, there's one, 8-bit number containing 3 ones. Or maybe I'll choose to put a 0 here, 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 and here. Right? But the order in which I choose to place those zeros doesn't matter. If I say, oh, I'm going to put some zeros here, and here, and here, and here, and here, I've got the same number as when I went here, 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 and here. So the order in which we choose these 5 zeros doesn't matter, right? So this is a combination question. It's the number of ways we can choose 5 bit positions out of 8 to have zeros, or the number of ways that we can choose 3 bit positions to have a 1. And so these should be the same, and in fact they are. They're both equal to 8 factorial over 3 factorial times 5 factorial. So how many 8-bit numbers have the same number of zeros and ones? 8 choose 4. 8 factorial over 4 factorial times 4 factorial. I don't know if BC does factorials. Nope. So 4320 divided by 24. $16.80 divided by 24, and there's 70 numbers that in binary contain the same number of ones and zeros. And so important note here, tied into a question that just came up. When you're doing questions with combinations, permutations, product rules, all of this stuff on tests or homeworks, always, write down something like that, or P, something like that. And always write down the formula like that, and then go ahead and calculate it. Okay? The reason being, the most common place to make mistakes, math errors, is in going from here to here. And that's the part I'm least concerned with. The part I'm most concerned with is knowing that you knew that this was a combination question, and knowing that you know how to use the formula for combinations to actually plug in numbers. So if all I see is an answer and that answer is wrong, you get 0 points on the question. If I see this and I see this and the answer is wrong, there's a good chance you're going to get full credit, right? Because I don't really care if you can use a calculator under time pressure without making mistakes. That's not my goal in this class, right? So always, let me know that you know that this is a question about unordered arrangements or ordered arrangements, right? And then show me that you know what the formula is. And most of the time you don't even need a calculator, right? Because if I were to expand this out, what would I get? I can write this out. Right? That's literally what it means. And all of these are going to cancel. And my 4 times 2, well, let's do my 3 times 2, cancel out with a 6. And my 4 and my 8 will cancel. So this will be 2 times 7 times 5. That gets me to my 70. So yeah, these are usually not too bad to actually work out by hand, but this is critical to have before you start doing all of this, and definitely before you write down that. All right, ready for the weird stuff? So the weird stuff is Pascal's triangle and binomial coefficients. And this is fun to play with and beautiful. So let's make the following arrangement of numbers. Let's start with the number 1, and let's just put a 1 next to each of those. And now we're going to fill out each row as follows. We're going to put a 1 in the beginning and end, and every number in the middle I'm going to write the sum of the 2 numbers above it. So 1 plus 1 is 2. And for my next row I'm going to put a 1 and a 1 here. 1 plus 2 is 3, 2 plus 1 is 3. And I'm just going to keep doing this. And you can do this all day. But I won't do it all day. We've seen that 70 recently. All right, that's probably a good place to stop for now. I'm going to do one more. All right, there's a good stopping place. All right, so this is called Pascal's triangle. And Pascal was a French, I believe, mathematician. Yeah, that's another story. All right, there we go. There's Pascal's triangle. Thank you. So it turns out, and we'll come back to this in a second, it turns out that each entry of Pascal's triangle is really just a combination, right? So this is actually 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, 3, 0, 3, 1, 3, 2, 3, 3, and so on. And each entry in this triangle is really just a number of unordered combinations. Row choose column, right? Where if this is our row R and this is our column C, the entry in row R column C is just R choose C. And this should work, right? 3, 0. Number of ways to choose nothing out of 3. Well, there's one way to do that. Number of ways to choose 3 things out of 3. There's one way to do that. 3, 1 would be 3 factorial over 2 factorial times 1 factorial. That's 6 divided by 2. That's 3. This is also 3. Well, there's your 1, 3, 3, 1 in that row number 4. So by just doing these simple additions, right, we can find the values of these fairly complex factorial formulas, right? N factorial over n minus r factorial times r factorial, but we can get them just by doing addition, right? So that's the first thing that's potentially interesting in this. So other things about this. So if you take a binomial like a plus b to the third, what do you get? You get a cubed plus 3a squared b plus 3ab squared plus b cubed. And these have a coefficient of 1 in front of them. 1, 3, 3, 1. That's that row of Pascal's triangle. If you want to do a plus b to the fourth, well, it's going to be, you know, some combination of a to the fourth, a cubed b, a squared b squared, ab cubed, and b to the fourth. What are the coefficients? 1, 4, 6, 4, 1. There's a plus b to the fourth. So if you have to do these exponentiations really rapidly, and you know the first few rows of Pascal's triangle, or you have a cheat sheet, right? It's really easy to write these out. And we'll wave our hands at an argument for why this actually works in a little bit. But it's not just a weird coincidence. There's a reason why this comes out, and it's something called the binomial theorem. Yeah, that would be handy in college algebra. All right, so that's one thing. If we take one of these rows and we add up everything in that row, what do we get? Well, you know, sum of 1 is just 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 1 and 4 is 5, and 6 is 11, and 4 is 15, and 1 is 16. What's our pattern here? Yeah, we're getting powers of 2. Now, why would that be? Why would adding up these big long things with factorials in them be giving us powers of 2? And think about what this looks like in a formula. Right, this is saying 4, 0 plus 4, 1 plus 4, 2 plus 4, 3 plus 4, 4 is equal to 2 to the fourth. And this is 4 factorial over 0 factorial, 4 factorial. and so on. And all of that, all those factorials and quotients add up to just 2 to the 4th. Which seems kind of cool, but possibly also kind of weird, right? But there's a good reason for this. So a few minutes ago, we looked at the number of bit strings containing a certain number of zeros. This is the number of 4-bit strings containing 0 zeros. This is the number of 4-bit strings containing 1 0, 2 zeros, 3 zeros, 4 zeros. And any 4-bit string contains either 0, 1, 2, 3, or 4 zeros. So the sum of the numbers of each of those has got to equal the total number of 4-bit strings, which is just 2 to the 4th. So there's another presentation of the fact that the number of ways to arrange 4 bits is 2 to the 4th. The number of 4-bit numbers is 2 to the 4th. And since each row of this triangle is the number of, combinations of 5 objects in this case, the sum of that should be the total number of ways to arrange 5 bits. That's 2 to the 5th. Don't even have to do the work. This is going to add up to 32. All right, what if we add the squares of the elements on each row? So 1 squared is still 1, 1 squared plus 1 squared is 2, 1 squared plus 2 squared, which is 4, plus 1 squared, that's 6. 3 squared is 9, so 1 and 9 is 10, plus another 10, this is going to be 20. 1 plus 16 is 17. Another 17 there is 34, plus 36, that's going to be 70. So if we add the squares on each row, we get 1, 2, 6, 20, 70. Well, this 1 is right here. This 2 is right here. This 6 is here. The 20 is right here. The 70 is right here. So the sum of the squares of the elements on row n is the middle element on row 2 times n. And that's kind of useful, or interesting at least. All right, one more oddity. So what's 11 to the 0? That's just 1, right, for whatever reason. 11 to the first is 11. 11 squared is 121. I'm going to cheat. I know this is 1331, but 11 cubed is 1331. 11 to the 4th is 14641. 11 to the 5th is 161051. But take a look at these first few. 11 to the 0 is 1. 11 squared is 11. 11 cubed is 121. 11 to the 4th is 1331. 11 to the 5th is 14641. So each row of this triangle gives you the next power of 11. And the pattern seems to break when we get to 11 to the 5th because it's 1, 6, 10, 5, 1, right? But that's because we're working base 10, right? And, 1, 5, 10, 10, 5, 1, if you were to actually write that out where this was, 10 in the hundreds place and 10 in the thousandths place, you would actually get 161051. So if you do this in a higher base, it actually works, you know, as far as you can go until you overflow your base. Yeah, why does that work? It's a good question to think about. My suggestion is take a number and multiply it by 11, do the pencil and paper, add and shift, and think about what's happening, and think about the way that we can describe the next row of this triangle by just adding the terms in the previous row. And that will probably at least convince you that there's a plausible reason why this works, and that it's not just pure magic. It's just partial magic. All right, one more Pascalism, and then we'll call it quits for today. But I want to play with binomial expansions on Friday and see why this is related to, you know, a plus b to the n. But I got to leave you with one more cool ism about this. So let's take a look at the nth rows of this. So let's call this row 1, 2, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and let's just start from row 2, and we're not going to look at these ones on the end. We're just going to look at all the numbers in the middle. Okay, so row 2, 2 is divisible by 2. Okay, so I'll put a check mark next to that. Row 3, the entries in the middle are 3 and 3. Both of those are divisible by 3. I'll put a check mark next to that. Row 4, well, the 4 and the 4 are divisible by 4. The 6 is not divisible by 4. So I'm going to put an X next to that. Row 5, the middle entries 5, 10, 10, 5. Those are all divisible by 5. So we'll put a check mark next to that. 6, 15, 20. Those are not all divisible by 6. We'll cross that out. 7, 21, 35. All divisible by 7. 8, 28, 56, 70, not divisible by 8. 9, 36, 84, 126, not divisible by 9. So what are the rows where every middle entry is divisible by the row number? It's the prime numbered rows. Yep, they always come back. All right, so that's Pascal's triangle. We'll dig into binomial expansions on Friday, but you've got enough now to actually do all of the homework questions. So work on those before Friday. Bring questions to class. We can run through those, and then we'll pull out an explanation for why this is related to expansions of binomials to powers, and that will do it for permutations, combinations. Then we'll go on to talking about recurrence relations, which will get us into some other good stuff. All right, cool. Have a good one. I will see you next time. Thank you.